All right. So in this lecture, we are going to talk about a new topic. So we are going to talk about the symmetry information about a crystal structure. So we call that crystal symmetry. Probably most of you have not access this type of knowledge. Okay. So let's start with some basic information about crystal structure. Okay. So the first concept I'm going to tell you is we call it crystal lattice. So what's a lattice? Okay. So lattice is a two-dimensional or three-dimensional network of identical points. Just this type of points. Okay. They're all identical. Okay. You can have two-dimensional or three-dimensional array of these identical points. That's a very general arrangement. We call that lattice. Okay. So uh, each point, right? So you can say because each point they are identical, then you can they can each point can repeat each other by translation. Just move this way or move this way. Each point. Okay, each point. So that's uh, the concept. The concept about lattice. Okay, that's crystal lattice. Okay. Then next, I'm going to introduce you a second concept we call unicell. Okay. So what's a unicell? So a unicell is a subdivision. So it's a kind of small combination of lattice point. So which can allow the you know the repeat the whole lattice structure through translation. Okay, through translation. Then you may wonder how we define a unicell. Okay, so for example, in this the net structure showing on slides. So we can have different choice of unicell, but you may wonder which one is right. Okay, which one is right? So we have green choice, we have red choice, and we have an orange choice there. So at least we cannot choose the orange one here, right? Why? Because you cannot repeat it, right? There's a hexagon unicell, but you cannot repeat it, right? Simply that's not the answer. And how about the green one and the red one? Then green one and the red one, they both can repeat the net structure by translation, right? But however, this one is also not a good choice. This one is good. The reason is for unicell we want to choose the smallest cell to repeat the lattice. Okay, that's the unit cell. Okay, that's a unit cell. Okay. So then, if we talk about 3D crystal lattice arrangement, so or lattice systems, so we have 7 basic options. So the first one we call that is triclinic. So you see in this triclinic, it's very simple. The shown here they're all unicell. Okay, so this is triclinic canonical unit cell, you can see here, the unit cell size, okay, here. So you have ABC. That's the side of the unit cell, okay. The dimension, uh, you know, dimension three, direction dimension for this unit cell, A, B, and C, and A, B, C, they are not equal. And also we use angle between the the side to define the the unit cell. So we have alpha angle between uh, B and C. Okay, B and C. We have beta angle between A and C, and we have gamma and between the um, A and B. Okay, A and B. For tricanonical cell, they are not equal. Okay, they are not equal to 90°. Okay, so then that's the we use this 6 parameter to define the net structure for 3D net structures. So then next one is monocanonic. So A, B, C, they are not equal, but alpha and the gamma angle, they are equals to 90°, but beta does not equal to 90°. Okay, so we have 4 parameters. Okay, unique parameter to define that. Okay, and also you can say, and we have orthorhombic. So even let's just put 1, 2, 3. Okay, we have orthorhombic, and we have rhombohedral, and we have tetragon, then we have hexagon, and we have cubic. And cubic has highest symmetry. Okay, if it besides you can see, because of the choice of the lattice pyramids, and as a in nature property, these unit cell, they have different symmetry properties, right? So you can say, in this one, we have for the monocanonic. Okay, for example, for the monocanonic, so we have a 2-folder rotation axis. Okay, for example, so what does that mean is with the 2 rotation, let's see. So you can draw a that's a C2. You can draw a C2 rotation axis here. Okay, and you can also have a mirror plane. Okay, you can also have mirror plane. Okay, and so mirror, you can actually have several mirror plane here, right? So you can you can to check the symmetry elements for other lattice structure. Okay, so let's do one more. Let's see, rhombohedral. So for the rhombohedral, so what we can have is, because since we have all the lengths of the unit cell are equal at 3 directions, then you can have a a 3-folder axis. Okay, so where that's diagonal between these 2 corners, then you can have a 3 rotations, C3 rotation. That's C3, okay? Okay, that's C3. So we will talk about the symmetry, a little bit more symmetry information about that structure later, okay? Then, so here, so that's a primitive, 7 that structure, okay? That is system. We have triclinic, monoclinic, and the hardest one is cubic, okay? So then if we add, okay, if we add additional point, at in this case monoclinic, we have if add additional dash point at this face and the bottom face, then we are going to have a base centered monoclinic, okay? Then we can do same thing for orthorhombic, okay? And also if we add a additional point in the center of the unit cell, then we can have called a body centered lattice structure, okay? Then for rhombohedral, we can have this body centered one. So for tetragon, we also can have this body centered tetragon lattice, and also for cubic one. So that's cubic body centered lattice structure. And also we can have the lattice point at additional lattice points on each face of the unit cell. Then we can have orthorhombic face-centered lattice here. And also for cubic, we can also add the face-based lattice point here, and then we can have cubic face-centered or face-centered cubic lattice structure, okay? So either way, okay? So then we end up with, extended lattice system up to 14. We call that 14 Brevis lattice system, okay? That structure arrangement, okay? Okay. So right now I have showed you what's a lattice. So what's unit cell and how to define unit cell, use, the length of the unit cell and the angle defined by between two length vectors, okay? And also by adding additional lattice points, we can have 7 primitive lattice structures, and by adding lattice points to the face body, we can have other 7 extended lattice structure in different class, okay? Total we have 14, okay? And here let's look at, so each type we can use cubic. We will use cubic lattice structure as example to show you concept called fractional coordinates, okay? For example, so if we define here is original point, then you can say at each side, so ABC, right? ABC. Then, so what's going on is, if we look at the coordination of this one, so we're going to have what? We're going to have, because if we define, C direction as, Z direction, okay, like a coordination system, is O and X, B is Y, okay. Then the coordinates of this point here is going to be 0, 0, 1. And this point, we're going to have what? We're going to have 1, 0, 0, okay. So these type of coordinates, we call them as fraction coordinates, okay. Then, since we said for next point, it follows translation to repeat the next point, right? So from here and from this origin point, if we translation along a direction by, you know, the unit cell length a, we can get this point, right? Then if we, uh, go z direction, move by the length of c, we can move to this point. Okay, that's translation. And for this body-centered cubic system, right? So what we have is, if we want to move this origin point to the body-centered net point here, okay, then we needed to do this, one half, one half, one half translation. So that's 1/2, 1/2, 1/2. That's the fraction coordinates for this body centered at this point. Okay, same thing we can deal with, get the fraction coordination numbers for the this face-based cubic net structure. Okay, net structure. Okay. So up to this point, so remember the next point we just in this you can call them abstract arrangement of points. That's that structure. The here the most smallest unit here, it's just simply as a point, right? No additional structure information, right? So another thing is we need based on the net structure, and we can show you how to count net point for each unit cell. Okay, so there are some basic rules. So if a lattice point in the body, then that point will count as one. Okay, if lattice point on the face in a face, because which is going to be shared by two cells, okay, then this face-based point contributed half point to each individual cell. Okay, if the net point at an edge of the unit cell, then that's going to be shared by 4 cells, right? Imagine that. Then this point will contribute as a quarter to each cell. If a lattice point, at the corner, then it's going to be shared by 8 adjacent unit cells. Then that point only contributes 1/8 to one unit cell. Okay, I hope you get that. Okay, and for example, and let's do a simple example first. Okay, let's draw anyone. Okay, right. So in this unit cell, okay. So all next point, they are we have 8 corner lattice points. Okay. Then, so let's say, how many, next point we count for this unit cell. Since they are at the corner, then each point can be considered as 1/8 to each unit cell. So then in this case, for this unit cell, we only have one next point can be counted. Okay. Then if we add a body centered next point here, then what do we have? So body centered here, so that's counted as 1. We are going to have 8 times 1 plus 1. We have 2 next point for this body centered cubic cell. Okay, so here are 2 real example shown here. A, B, they are real quick structures. Okay, for cesium chloride salt and the zinc sulfide salt. Then in this case, in this um, uh, cesium chloride salt, so okay, cesium is in the center of it's a body point. Okay, then we know we're going to have one cesium in this unit cell. Then how many chloride? So all chloride they occupy the corner. Then we have 8 times 1/8. Okay, that's for chloride. Then you are going to have, cesium chloride. That's going to be the formula for this unit cell. Okay, then you can do same calculation to get what's a formula for this unit cell. That's a zinc sulfide material. Okay, so that's how we count the net point for different structures. Okay. All right. So as I showed you, okay, up to this point, okay, we only, talk about net structure, consist with, these simple dots, okay, simple dots. So record the group theory we talked about so far. So remember, for different object or for different mode structure, so we can have, basically we can apply 5 different, symmetry operations, and then we use the procedure. We can define the point group, or we can define symmetry properties for an object and a molecule, right? So record that information. So then, think about the real crystal structure. So actually, each lattice point can be replaced, by a real motif. Okay, the motif can be a molecule or part of a molecule. Okay, then think about it. If we put a molecule, replace this simple dot, then what we're going to have for each molecule, right? Each molecule is going to have its own symmetry information, right? Then besides lattice, structure information we have talked about, then you are going to have additional symmetry information for each point here. This is molecule, okay, right now. Then for each point, then we're going to have lattice symmetry. We call lattice symmetry because right now each point is a real molecule. Each molecule has its own symmetry, defined by these 5 different symmetry operations. Okay. But in reality is for lattice point symmetry, we only consider 4 types. Okay, 4 types. So, corresponding molecular symmetry, we use N to express rotation for the molecule in the crystal structure. And we also have reflection. We don't use sigma, we use letter M to express reflection in the crystal structure. The molecule in the crystal structure, okay? That's molecule-based symmetry property. And we use, the one, this term, there's a dash, with that number 1 below. We define that inversion symmetry for the molecule occupy the single next point. And also we have an improper rotation, but here is I want you to emphasize. So we use dash n to symbolize improper rotation. In addition, for lattice point symmetry, okay, the improper rotation is defined as rotation followed by inversion. Okay, it's different from molecular symmetry we talked about before. For molecular symmetry, improper rotation it defines rotation followed by reflection. We can call it rotation reflection. But for improper rotation, for the united point symmetry in crystal structure, we call that rote inversion. Okay, they are different. Okay, they are different. So this one they are different. Okay, but the other three, they have same identical meaning but different symbols. Okay, different symbols. We don't use E here. We don't use E here. Okay, for lattice point symmetry. Okay, we don't consider that. Okay, even we still have that, but we don't consider. It's no need to consider identity for lattice point symmetry. Okay. Then let's move on. Okay. Then we're going to have what? Okay, for each lattice point, when you replace, that point with a real molecule or part of a molecule, and which going to have its own, different symmetry information. Okay, then because the nature of the crystal structure, we're going to have 32 point group. Okay, we call it crystal point group. Okay, and which corresponding to molecular point groups showing on the bottom. So remember, to define the symmetry for molecular point group, we use Schroff-Lie notation. Remember C1 group, Ci group, CS, C2, C2H, and O group, OH, tetrahedral. Remember, get your memory back. Okay, then we can get corresponding 32 crystal point groups. Okay, then the term we are using here, we call it Hermann-Mauguin notation. Okay, Mauguin notation. And so the one here corresponding to C1, because if you just look at the symmetry information at the molecular level, so they are corresponding to each other. Okay, they are corresponding to each other. Okay, and so the let's see, the OH here, and we are going to have M3M in the we call that M3M for in the class of crystal point groups. Okay, so here is molecular. Okay, molecular, and here is crystal point group, but they are top of theme saying for molecule based symmetry. But one is individual molecule, another one in crystal we talk about the molecule in a three-dimensional structure. I hope you get the point. What is the difference between them, but what's the same thing between them? Okay, all right. So I'm going to show you example how to read these Hermann-Mauguin notations. Okay, I will give you examples and in next slides. Okay, sounds good.